Morning. So the last presentation of the day. Feels good, right? My name is John Volkering. I work for the IP and broadband division of Ericsson out of the Netherlands. And in this presentation, I'm going to touch a slightly different topic as what you've been hearing most of the time in the last couple of days. Where in the last couple of days, it was typically about, DNS, BGP, IPv6, that kind of stuff. In this presentation, basically, we are highlighting the technology that can be used to actually bring the traffic to the core, to the IP core, where you typically use all this kind of technology that we've been discussing here. An MPLS TP could be a technology, an emerging technology that could take an important role in that. So in today's transport architectures, it's typically built out of a layered approach. Typically, every transport network has an underlying optical layer, which typically has DWDM kind of equipment to optimize the capacity of a single fiber. In this DWDM, typically the operators are running SDH or SONET services to actually transport legacy as well as Ethernet traffic. The Ethernet traffic that is used to, at the end carry the IP traffic can be either natively transported over the optical layer or encapsulated into SONET or SDH. And then finally we have the core, which is a pure IP core typically. I'm sure everybody recognizes this layered approach. So if we want to evolve this layered approach, what are the transport characteristics where we need to look for in order to make it better than what we have already today? So first of all, in today's architecture, many of the things we've been using are well proven. So we should not change the things that are actually turned out to be working. And one of the things are that the transport characteristics that we take from today's optical and SDH and SONET infrastructures are statically provisioned and are bidirectional paths, right? So today's infrastructure is also carrying multiple different type of traffic, like TDM or packet traffic. So networks are always subject to failure, node failure, fiber cuts. In such a situation, we need to provide a backup path. This backup path has to be predetermined. If the backup path is not predetermined, then the backup path may be routed over links that you don't like, because those links may already be full, those links may have limited capacity, or those links may have been reserved for other capabilities rather than taking the role of the backup path. And the transport networks are highly automated. So last but not least, in order to build a next generation evolved infrastructure, you need to rely on automated OEM capabilities to deliver you the fault management capabilities that are actually needed for operating a large transport infrastructure. Having said that, the different layers will evolve into a consolidated infrastructure where only an optical layer will exist. This optical layer may be extended with an OTN layer to provide forward error correction or grooming capabilities to better utilize the fibers. It then typically will use an MPLS encapsulated infrastructure to better leverage the statistical multiplexing capabilities that we have with MPLS. And then finally, IP and Ethernet packets will be routed over that. So where those different layers are consolidated, the same consolidation will typically take place also from a product point of view or from a system point of view. Where we before had multiple different products to do these different layers, what we see is that they will be consolidated into a single infrastructure, single systems. So as mentioned, MPLS-TP is the evolved technology for the transport network. What is that actually? Actually, it's just a subset of the existing MPLS that we know already today. What we have been using for many years, supported by IP, and therefore it's often been called IP MPLS. The MPLS-TP has, it is a subset of MPLS, as I said, so it's using the same infrastructure, the same packet format as existing MPLS, and therefore it's quite easily interworkable with existing IP MPLS. Also, it's relatively easy for the existing IP MPLS equipment to embed MPLS-TP capabilities because they already have this kind of labeling structure supported in the hardware. And then obviously there is some additional functionality added to that. So what additional functionality is what we see on this slide. So we added transport-like OEM. What does it mean, transport-like OEM? Basically, it's the in-band capability of transporting the OEM packets. We had to add more stringent performance monitoring capabilities than what that was existing in today's IP MPLS infrastructures in order to support alarm and fault notification. So then what was also an important requirement for IP MPLS that is being added in this additional functionality is the fact that it has to support transport-like operations. Today's transport networks are typically being provisioned statically through an out-of-band NMS system. This has the advantages that it is typically a very robust environment that can scale quite easily to a high number of nodes. And also transport-like means bidirectional paths, where in IP MPLS an LSP is unidirectional. This MPLS-TP has to support the bidirectional LSP capability also. And obviously, like we had with the traditional legacy transport networks, we need to have similar resiliency capabilities. SONET and SDH are well known for their 50 millisecond service restoration. So if we build something new, then at least it should have similar capabilities and not worse. So that's been done also in MPLS-TP additional functionality requirements. As said, MPLS-TP is using exactly the same MPLS data path that we know from IP MPLS. So the same labeling structure, the same labeling formats, the same technology for doing the forwarding with the labeling push, pop, and swap capabilities. Next to that, as mentioned already, and I will come back to that in more detail in the next couple of slides, transport optimized OEM. I think that is one of the most important enhancements that we make into MPLS-TP. Connection-oriented, where transport networks typically provide back-to-back, point-to-point connectivity from an access network down to a core. We would like to have this connection-oriented and not connectionless. This is because a connection-oriented network is an infrastructure that is basically the only one that is quite easily manageable from an operational point of view. Yeah? Point-to-point means you put something into the tunnel on one side and it has to come out on the other side. If you have multi-point capabilities, you may put something into the tunnel on one side, but you never know where it comes out. So therefore, connection-oriented is quite an important requirement. And it has to support the transport-centric operational model, meaning that it's not depending on a distributed control plane only, but it should also support a centralized control plane by the means of an out-of-band NMS system. and obviously the protection switching capabilities of MPLS-TP triggered by OEM. So I mentioned already OEM is a very important enhancement into MPLS-TP from existing MPLS, and this is done for the failure detection that can also trigger the restoration. So let's look a little bit more in detail on the transport optimized OEM capabilities that we added into MPLS-TP. Basically, MPLS-TP has the capabilities of monitoring the transport network, and it has the capabilities of monitoring the services network, so the real service that you deliver to a customer. So when we talk about the transport network itself, it can be most easily be seen as the LSP. Yeah, the LSP that is actually carrying the service of the network. And the services typically are pseudo wires, or actually they're always pseudo wires. Yeah. So the transport optimized OEM has a capability of transporting OEM traffic embedded in the data path of the user traffic. So the OEM traffic will always follow exactly the same route as the user traffic. And that is very important because with this you can get very good service layer agreements on the services itself. How is that done? That's done by associating the data path with the OEM packets. And that's known as the associated channel. So inside the LSP, a channel is created that can carry additional information like the OEM traffic. And that's called the associated channel. The associated channel for pseudo wires is something that actually exists already for quite some time, even before MPLS-TP existed. Basically, the IETF had the intention to reuse the same infrastructure that has been used already for this kind of capability, enhance it, that it can also be used to carry the associated channel over the LSP itself. And that's called the generic associated channel. And that's defined in RFC 5586. So how does it look like? So I'm sure you recognize this, this stack, an LSP label, a pseudo-wire label, and then on top of that, in a typical pseudo-wire environment, you will get first the control word. And the control word is always been 4 zeros. So in this particular case, because it's not a control word, it's not a normal pseudo-wire service payload, but it's an associated channel for the pseudo-wire. The first NIBIT is not 4 zeros, but it's 3 zeros and a 1. That basically identifies that the payload in that particular packet is an associated channel payload. And we've done something similar for the LSPs, for the generic associated channel. So where we had the LSP that already was carrying, for example, a pseudo-wire, there is a new reserved label introduced in MPLS-TP, which is reserved label 13. This label is known as the GAL, or the generic associated label. So what does this label basically do? So when the LSP reaches its endpoint, typically the label, the outer label will be pushed, or will be popped. When the outer label is popped, the inner label is exposed to the system. So if the inner label is a GAL label with the level 13, with the value 13, then basically it's been exposed to the control plane of that particular device. And the control plane will detect that it is an OEM payload packet and will process it accordingly. So as long as the LSP label is not being popped, the GAL will not be exposed, and therefore the OEM traffic will not be exposed to the control plane of the nodes that it's passing through. So where can we apply these OEM capabilities? Well, as I said, it can be applied to the pseudo wires, which is typically the end-to-end service between the attachment circuits of the provider edge routers. It can be applied to an LSP, which sits between those two provider edge routers, but it can also be applied to a portion of LSPs. And if that's the case, then we're going to mesh the LSPs into a hierarchical model. And it even can be applied to a section, and a section is nothing else as a link between two routers. Yeah? So the features that we can run over the OEM are clearly the continuity check capability. The continuity check capability is being used for triggering the restoration if a failure is detected. It can also be used for connectivity verification. When the service is not working, you may want to find out where it gets broken, and then with the connectivity verification capabilities, you can actually find out the point where it goes wrong. This connectivity verification capabilities is quite similar as what we know from traceroute, for example. And then furthermore, there are capabilities introduced to actually get delay and loss measurements, as well as failure notification capabilities. And this is all being carried over the associated channel, so in-band together with the user data. So I mentioned already the connection-oriented capabilities. So because the OEM is running over the data path, it's very important that every single packet is carrying exactly the same path all the time. Therefore, ECMP is being excluded from MPLS TP. With ECMP, the traffic may, be balanced between different routes throughout an infrastructure, but that results that maybe one route is working and the other route is broken. So therefore, it must be excluded. For the same reason, also multi-point-to-point capabilities are excluded, as well as PHP. So if PHP is enabled, then the LSP doesn't reach all the way till the far end where the termination point of the service is. So therefore, the last label should not be popped by PHP, and therefore it must be disabled by default. And also, it introduces new LSP types. So where with IP-MPLS, we typically know only the point-to-point and point-to-multipoint unidirectional LSPs. With MPLS-TP, also bidirectional point-to-point LSPs are supported. In two different flavors, associated, meaning the transmit and the receive are carrying exactly over the same path, or co-routed, meaning the endpoints are at the same, but they use a different path for the transmit as well as for the receive. So I mentioned transport-like operations. Typically, the infrastructure from the existing SONET infrastructures are also being managed with an out-of-band NMS system that actually does the provisioning. This out-of-band NMS system typically has a topology view of the infrastructure, and it uses this topology view to provision the paths throughout the network by contacting every single network element in the path and provision the LSP label swapping in that particular point. In order to get this out-of-band topology, we can again leverage the associated channel to actually carry additional information, and this additional information can be used for DCN capabilities. But it can also be used in order to get the topology view. For example, you can run over this associated channel over this MCC, this management communication channel, an OSPF protocol, and using a Dijkstra algorithm and run SFPs to actually get a link state database of your network. and that link state database is then being used by the NMS to provision the paths. So if something is changing in the network, for example, a new node is being added into the infrastructure, this is being automatically learned by the NMS, and the NMS can then pick this new route also for enabling new services. So the protection switching, as mentioned, we are sending OEM packets between the two endpoints in order to figure out whether the endpoint is still there. So if the endpoint is no longer receiving to the OEM request, then basically the protection switching or the restoration capabilities can be triggered. This works in a very similar fashion for the pseudo wires as well as for the LSPs as well as for a subsection of LSPs. And basically it is as simple as it is shown on the picture. So there is an OEM between the two endpoints. If one primary path is detecting a failure, it's using a simple signaling protocol which is called the PSC between the two nodes to basically tell both ends, okay, there is a failure on the primary path, please switch to the backup path. Yeah? This can be done for a 1+1, so meaning that the recovery path is already sending the data, so the data is replicated at the source, or a 1-to-1, where the recovery path is actually in standby until the source says, okay, now we switch to the backup path. So where does this technology fit the best? As mentioned, it's been used to scale up the infrastructure, to get an infrastructure that scales with a similar method as what the existing transport capabilities like SDHs and SONET are currently doing. So therefore, the technology fits very well in the transport area of the entire infrastructure, where we believe that in the core of the infrastructure, IP MPLS will be predominant because of its flexibility of its implementation. So how can we build then services with MPLS-TP end-to-end? So I think these services are quite common. So you typically would like to have an E-line, ELAN, E3, or an IPVPN kind of transport service from somewhere in the access to somewhere in the core or to another place in the access. So having IP MPLS in the core and MPLS-TP in the transport layer, typically you terminate the, for example, IPVPN at the edge. So from there you have a layer 2 point-to-point path using a pseudo-wire technology all the way to the access. So the IP VPN capabilities does not have to reach all the way to deeper into the aggregation all the way to the access. This is simplifying the infrastructure a lot. So if there is a requirement to actually have a service that starts somewhere in the IP MPLS environment and gets terminated in the access where it's an MPLS-TP, because it has been MPLS-TP is being based out of the same principles as IP MPLS, it can be quite easily being interworked. So for example, in this particular example, we're using multi-segment pseudo-wire capabilities to stitch two pseudo-wires from the dynamic provisioned path and the statically provisioned path together into the PE, into the edge. It can also be done with single segment pseudo-wires, but for that the LSP has to be stitched at the same place instead of the pseudo-wire. And that concludes to the summary of my presentation. So we all know that networks are under a constant transformation. There is new technology like MPLS-TP, OTN, and POTP that will enable the transport evolution to be to get a more simplified infrastructure, consolidated into as few as possible layers in order to reduce the operational and expenses of an service operator. So that concludes my presentation.
Okay, any questions for John?
Hello. Hi, Dan White with GlobeNet. OTN has an existing service channel already. Could you describe the relationship between that existing OTN service channel as well as compared to the MPLS TP associated channel?
It's quite similar. I don't know exactly how the server channel of OTN looks like, but what I learned is that it's also quite similar as how SDH and SONET are currently operating. So I don't know the exact format of the packet, but it can be assumed that it's a similar implementation.
Okay, anybody else?
Hi there, Rob Shakir from Cable and Wireless.
Hi.
So I've got an existing MPLS-T network, and it seems to work okay, and this sits in the same kind of space, right? Yep. There's a lot of overlap. So also following the IETF process, do you feel that the amount of work that's going in the IETF justifies building the MPLS-TP separately rather than as a set of extensions to MPLS-T that just sat in the IETF?
Well, yeah, there is a lot of politics in this area, as you probably be very well aware of. Whether it justifies or not, we have a different ways of doing this. MPLS-TP is one of them. Extending IP MPLS all the way to the Axis is another one. Personally, I feel that comes with more challenges as building a similar infrastructure than with MPLS-TP, because it can be quite challenging to build an IP MPLS infrastructure running a huge IGP to support thousands or 10,000s of nodes and 10,000s of links. I'm not saying it's not doable. IP MPLS and the IGP that we use, ISIS or OSPF, are capable of building very significant infrastructures, but it comes with a complexity, right? And MPLS-TP is basically trying to address this complexity by outsourcing the complexity to a centralized NMS system. And this principle has been shown to be working based on the legacy infrastructures that we have today with SONET and SDH. So yes, I think there is room for many different flavors of building an evolved packet transport. There is a lot of attention in the industry on MPLS-TP nowadays because of the smooth interworking with existing IP MPLS and the flexibility to make it scalable to support networks in 10,000s of nodes.
I think it's a good point. The centralized thing is actually, I think, as your TE network grows, you work out this idea of a dynamic path. It's actually pretty hard to manage.
Exactly.
So that's why there's people like Coriden here, I guess, and people like Wandel building products that basically take our IP network and go, hey, let's overlay some paths on this and let's do it offline because it's easier that way.
Yeah. That's the way how we do it with traditional, legacy infrastructures for a long time. So, yeah. It relies a little bit more on the centralized NMS system, obviously, but that's only a single point in the network, and it's not everywhere distributed throughout the entire cloud.
Cool. Thank you very much for your answer.
Thanks.
Okay. Thanks very much, John.